Earlier, if you look at the meteorological tools, the croaking frogs have long been regarded as the indicator of good rain. But if you look at nowadays the frogs, you cannot find any frogs anywhere. So that is the amphibian species are under the verge of extinction. So 40 years back, we could able to forecast some event 3 days in advance. Now we can able to predict that even 5 days in advance. So that is the meaning of this forecast skill improvement. Actually, weather forecasting is a global effort, the collective effort under the UN framework. So that's why you cannot blame anyone for a wrong forecast. Today, I'll be talking about recent advancements in climate modeling, which is able to save livelihood, not only livelihood, to some extent the economic loss also, because to some extent we can limit the economic loss due to extreme weather events if we have advanced forecasting of the event. So I'll be briefly covering about the history of weather forecasting and the recent advancements in the numerical weather forecasting and the future of weather prediction. So this is a famous diagram which shows that this is known as the disaster paradox over the last 5 decades. So this is the this figure shows the decade-wise disasters from 50 to 65 and then 66 to 75 and the recent decades. We can see that worldwide the disasters have been, or extreme weather events have been increasing. But at the same time, if you look at the death rate, the number of deaths due to disasters, it is drastically reducing. So this blue color represents the hydrometeorological disaster, which is connected to the climate. So this is where we have to think about why this death rate, though the disasters are increasing or the extreme weather events are increasing, but we could able to limit the death rate to a considerable extent over the last 7 decades. So that is what the core of this talk today. So if you look at the climate related risk, risk is a function of hazard. Hazard is nothing but any kind of climate events, extreme weather events, and then exposure and vulnerability. So this exposure part is nothing but the number of volume of people, asset, etc. is being exposed to a particular event, hazard. And then the vulnerability is mostly connected to the socio-economic aspects of the sensitivity of the people who are exposed to these hazards. So meaning that the socio-economic aspect determine the vulnerability. So already there are many socio-economic aspects which leads to the vulnerable communities. So when it comes to disasters also, these vulnerable communities are more exposed to the hazard in terms of risk. So that is why the socio-economic aspects very much connected to the total risk of related to any kind of climate events. So in this case, what we can do is that we cannot stop hazard, we cannot stop any kind of extreme weather events. What we can do best is that we can improve our ability to monitor or forecast the impending onset of the hazard. That is known as early warning system, EWS. So if you have a better early warning systems, forecasting systems, we can limit the hazard or the we can limit the hazard to become disasters. When the hazard become disaster, it has to meet with the exposure and the vulnerability part. So that means what best we can do is that we can forecast this type of extreme events well in advance, so that we can at least save the life and to some extent the livelihood and to a greater extent the economic loss or as a total loss or the total risk associated with these hazards. So the present the focus of today's talk is nothing but how to develop early warning systems. So if you look at the climate change, the hazard is there. If climate change is making most of the hazard more frequent and more intense. So this is how earlier time also there were a lot of hazards in terms of lightning, floods, storm surge, droughts, heat waves, cyclones, tornadoes, etc. But in recent times, what is happening is that both the frequency and its intensity is increasing. So the hazard is becoming more frequent or more intense. So directly it is connected to the risk, because if hazard intensity and frequency is increasing, risk is also directly increasing. Not only the hazard, the vulnerability part of this hazard and the exposure part of this hazard, this risk connected to climate events are increasing. So not only the hazard itself is increasing, the vulnerability of the community is also increasing due to recurrent climate events, and more people and more spaces is getting exposed. So as the climate change and extreme weather events are expanding to many geographical areas, so there the more exposure itself is increasing due to climate change. So that is why everything is connected. So what ultimately we want to do is that we have to reduce the composite risk associated with the hazard, vulnerability, and exposure. So that is why if you look at the global framework, we have 17 sustainable development goals. But if you look at the all 17 goals and the 197 targets associated with all these goals, the climate action, the goal number SDG goal number 30, which is nothing but the climate action, which is the center of the all 17 goals. So that means the climate action actually connect or determines the achieve whether the other goals are being achieved or not. Because if you look at the no poverty, the goal number 1, the no hunger, goal number 2, decent economic growth, the good quality education, equality, gender equality, sustainable cities and clean energy, or the decent economic growth, or in terms of sanitation and the water. So everything is connected to climate. That is why climate action is the main goal in the SDG, which connects to all other goals. So here, how to deal with this climate changes and how to responding to this climate changes. There are two ways by which we can respond to climate change. One is the mitigation, and another is adaptation. The mitigation is nothing but we have to stop the core problem at the root level, because it is nothing but emission, the fossil fuel emission, which is creating all these global warming issues. So we have to cut down the fossil fuel emission. So we have to devise a lot of alternate energy sources, or we have to depend on clean energy to reduce the fossil fuel emission to the atmosphere. So that means we have that is a kind of long-term approach. But in terms of adaptation, when it comes to adaptation, the emergency and disaster preparedness is the main thing, which is and also in terms of the agricultural sector, health sector, this sector has to get adapted to the changing climate pattern. So, and ultimately there should be a lot of synergy which is linking this adaptation goals with the mitigation goals. So that means it is not isolated, or it cannot be handled in silos, but whatever adaptation strategies we devise, it should have kind of long-term goals and plans. So that means in terms of disasters, if you look at the worldwide, it is increased 5-fold over the last half century. So that is like last 50 years, the worldwide disasters have been increased 5-fold, 5 times. So that is why if you invest 1.6, this is just a rough estimation, global estimation, 1.6 trillion US dollar if you invest in early warning systems, the total benefit, the total gain we are getting out of this would be 6.4 trillion US dollars. So that is the economics. That's it. Everything is connected to economics also. So now coming to the inequality part of the disasters, it's nothing but if you rank the total number of disasters happened over the last 70 years and rank them according to number of deaths, we can find that the top 10 ranks, they are belonging to developing, underdeveloped or third world countries or the Pacific Island nations. Because if you look at 1983 drought in Ethiopia, it took almost like 3 lakhs people life. And recent Myanmar cyclone in 2018, Nargis, that claimed almost like 1,50,000 people's life. And that is why if you look at this, the name of the countries which is ranked according to the number of deaths, it is most of the underdeveloped countries are coming first. Ethiopia, Bangladesh, Sudan, Bangladesh, Myanmar, Ethiopia, Mozambique, like that. But if you come to the, if you rank according to the total economic loss, we can find that the top 5 to 6 places is occupied by United States, because they have a lot of economic development, so that naturally if a disaster happens, their economic loss will be very high. So if you look at starting from 2005 onwards, the hurricane Katrina, Harvey, Maria, Irma, Sandy, Andrews, all these hurricanes claimed almost like €1 trillion together, $1 trillion loss. So earlier the hurricane related loss was very much limited to $100 billion, but altogether composite in in maybe 2-3 years, the total compound loss is something around $1 trillion. So this is how the economic loss is increasing. But the inequality part of it is that if you look at the climate change aspect, because the climate change is mainly because of the increased use of fossil fuel starting from the Industrial Revolution 1860 onwards. All this, if you count the amount of carbon dioxide right now in the atmosphere from pre-industrial period onwards, you can find that 70-80% of this carbon dioxide is being dumped to the atmosphere by developed nation for their developmental activities, economic growth, which is driven by fossil fuel. So that is the main thing behind this. But the most livelihood loss and life loss is happening in the underdeveloped countries. So this is the dilemma, and this is the inequality. So though they are not taking part, they are underdeveloped, they are not taking part in this global warming issue, but they have to bear the heat of all this global warming issues. So this is where the inequality rises. That is why if you look at the COP, Conference of Parties, which has held, the recent one which are held in Baku, Azerbaijan. So where in the COP29, that is why the global nations, especially the developed nation, now realized their responsibility in making this global warming issue, and they come up with a solution to generate a kind of fund with a new collective quantified goals, which is nothing but they have to secure almost like 300 billion US dollar by the developed nation to give to the developing nations to prepare for mostly for their adaptation and mitigation activities. So this is what the good sign of it, but they realized and they are contributing. But the recent Trump government came to the office, and his remarks and his actions are now not promising. So maybe he is going to shut down many of the climate modeling centers in US. So that is going to affect globally. So that is another part of the story. But otherwise, another demand is that if you look at the total loss around the world from the developing nation, it accumulates more than $1 trillion US every year. So this 300 billion US dollar is nothing in front of the total economic loss or the total loss. So that is why they have to the UN has to find out some other way to accumulate this much amount through private and public participation, and to collect almost like maybe it is estimated that 1.3 trillion US dollar per year is required for this adaptation activities which is planned. So that is why the main thing which came out of this loss and damage fund, it is known as loss and damage. From that loss and damage from fund, they are trying to make a program called early warning for all. Early warning for all is nothing but as the previous UN Secretary Antonio Guterres, they rightly pointed out that less than 1/3 of the developing nation is not having access to better early warning system till now. So that is why the early warning for all, which is nothing but which call for every person on the earth to be protected by the early warning system. The ambition is to be achieved by 2027. That is the target. But in this devising this early warning system, there are different pillars associated with this early warning system. First is nothing but the disaster risk knowledge. First is the disaster risk knowledge. The people, the community should be aware of what type of disaster they are going to face in future, or the geographical vulnerability or the geographical exposure to the hazard. They have to know. So first is education awareness part, and then second pillar, which is belong to the climate modeling and the forecasting and meteorology climate modelers, which is nothing but detection, observation, monitoring, analysis, and forecasting. So through various modern techniques, we have to forecast the events well in advance. So that is the pillar number 2. Pillar number 3 is nothing but warning, dissemination, and communication. The communication is very much important. That is very much critical. So whenever there is kind of forecast or approaching disasters, it has to be properly communicated to the public. So that is why the core essence of this dissemination, warning dissemination, should be properly communicated to the public without any kind of confusion, at the same time by adding accommodated uncertainty as well. So that is why the pillar number 3 is very much important. And then the pillar number 4 is nothing but preparedness and response capabilities. That is why we normally do this after every disaster, like post-disaster need assessment and the assessment of the disasters, what was lacking and what is going to be done in the future. Like that, we have to prepare for the event. It is a kind of disaster preparedness. So these are the 4 pillars of which constitutes the better early warning system for all. So the target is, like, if you look at the history, we can find that this WMO, World Meteorological Organization, which is celebrating 75th year, starting from 1950 onwards. This year's motto of the World Meteorological Day, which is normally being celebrated 23rd March every year. So this year's theme was nothing but closing the early warning gap together. So it advocates for better early warning system, at the same time the global cooperation. So that is where the dilemma, where the Trump government is trying to step back from the committed role. They are like NOAA and NASA, all these climate related agencies, which is playing a critical role globally in this early warning system development and the dissemination. So that is what the world is moving in a very uncertain time. So this is also going to affect all our climate related activities. If you look at 1950, in 2015, so that is the in 2015, after Paris Agreement only, this early warning system for all concept has been formulated. So that time only 52 nations were having the access to this early warning systems. But now if you look at 2023, almost double, 108, almost double the countries got the capability of this access and the inbuilt capability of this early warning system. So this is how one of the major achievement of World Meteorological Organization, which is part of UN. So through which we are all global nations, they are working together to make a very good early warning system which is accessible for all. So that is why this year WMO Day is being celebrated with a theme, closing the early warning gap together. So global cooperation is very much important. So that is why if you look at the early warning system and disaster preparedness, this is a traditional approach. When a disaster happens, everybody is running out of that site. So that is after the occurrence of the disaster. But with enhanced approach and by using the early warning system, that leads to early action. When a disaster strike, we can escape well in advance from the disasters, and after the disaster we can have very good response to the system without, if there is no death associated with a hazard, then we can easily go back and rebuild. So that is why enhanced approach is nothing but which is depending on the early warning and early action. Early warning alone will not solve this problem. That based on the early warning, early action should be there at the local level. So that is also very much important. So when how we can build this type of early warning system? Earlier, if you look at the meteorological tools, the croaking frogs have long been regarded as the indicator of good rain. But if you look at nowadays the frogs, you cannot find any frogs anywhere. So that is the amphibian species are under the verge of extinction. That is another aspect of climate change, because climate change also trigger a lot of extinction events earlier also, but this time the global warming induced extinction crisis is also large, in which amphibian species are more vulnerable. Almost like 30% of the amphibian species are under the verge of extinction. So that is another story. But when it comes to now the modern tools like the supercomputers and satellites, radars, all this is our weather prediction tools, modern tools, through which utilizing all these tools we are making the forecast. So weather prediction is nothing but we have to predict different type of weather systems. Like for example, there is cumulus convection, small scale clouds, and then large scale cyclones, the monsoons. So this system has characteristic time scale and space scales. So based on which we are predicting. Actually, these are the target in the weather prediction. If you look at it, it is kind of shooting problem. The target, the shooting problem, first we fix the target, and then we select the tools according to the target, the size of the target and the distance of the target from the shooter. Like that, the time scale, the size of the meteorological phenomena and the time scale of the meteorological phenomena, which both together determines which type of forecasting tool we want to use. So that is why weather forecasting is a kind of shooting problem. Based on the target, we determine if you want to predict monsoon, you have to take a very one tool. So it is a kind of ensemble or the climate coupled models. But if you want to predict a local level convection, with the radar we can forecast the nowcast the occurrence of a convective system or lightning. So this is how, based on the target, we are selecting our tools to predict this. The characteristic of the targets, such as the aerial extent, how big is the phenomena and how long it will last. These two aspects, like this time and space scale, will determine which type of tools we have to use to predict these systems. So that is why if you look at it, there are different ranges of forecast. Like for example, monsoon forecast. Monsoon forecast. Recently, IMD issues monsoon forecast for the entire monsoon season, starting from June, 1st June to 30th September. The compost, what is going to be the seasonal scale monsoon rainfall throughout the India, through pan India. So that the monsoon forecast normally is being issued for pan India. The time scale is like few season, one season, like few months. And when it comes to medium range forecast, like for example, maybe what is going to be to happen after 10 days or within 7 to 10 days. So that is the focus of medium range forecast, where if there is any chance of occurrence of a cyclone or very big cloud systems, or so that is very the in the medium range forecast we are focusing over a smaller regional region, and that is valid for 10 days, and for short range forecast which is valid for 1 to 2 days, so that is for a much smaller region, like for example a state, and then 6 to 12 hour forecast. That is, in that time scale we are forecasting actually the thunder clouds, lightning, and cloud burst and all. That is valid for 6 to 12 hours, but available and representative for a very small local region. So that the tool for those is nothing but the satellites and radars. So now, when it comes to NWP process, there are few things how the forecasting is possible. So what is a forecast? If you look at any variable f in future time, that is a function of, that is a combination of value of that variable at present and then the change in that variable in a definite time. So that is what, if you want to estimate the change of that, for example, temperature, change of rain pressure, change of wind speed in future time, maybe a small time step. So that if we can find out, adding that to the present state, that will give the future value of this variables. So this is the fundamental in weather forecasting. So what I want to say here is that in order to predict the weather for the future, what we need is that we should have the present status. We should know the present status of that variable at the initial time. So that is commonly in the NWP it is known as initial condition. So all this weather forecasting problem is formulated based on physical laws. So all these physical laws have been solved not analytically, it is solved numerically, because there are a lot of non-linear aspects or the non-linear equations which is having a lot of unknowns. So there is no exact solutions available, so that you have to depend on numerical methods to solve these equations. So this is why the crux of NWP problem, it based on science and physical laws. The fundamental physical laws which to be is used in NWP problem is nothing but Newton's second law, that is the three component of wind like U, V, W, X, Y, Z direction, wind, and then conservation of energy, which determines the first law of thermodynamics, and then ideal gas equation of state, the conservation of mass, and conservation of water. So these are the 7 fundamental equations on which we are building the NWP problem. So this is based on physical laws. We are assuming that our atmosphere is a fluid, so which obeys all these physical laws or the laws which is applicable for the gaseous phase of the matter. So that means all this 7 equation has to be solved at each and every grid point, each and every point on the Earth's surface. So every point, not only at the surface, at different height levels, altitude levels, and to different depth levels in the ocean has to be solved with all this equation has to be solved at each and every grid points. So for numerical weather prediction, we need initial state of the atmosphere and closed set of prediction equations. So these prediction equations are known as prognostic equation because it is trying to find out the value of the variable at a future time. So that is known as prognostic equations. So now, and a method to integrate that equation in the future. So this constitute all NWP problem. So there are a lot of history because in 1904, Jetness formulated this problem, but Richardson tried to solve this, but he miserably failed. Instead of getting 2 HPA pressure difference in at a European station, he got almost like 145, 2 orders of magnitude higher. So his calculation failed, and also not only that, because he tried to make a 6-hour forecast. For that 6-hour forecast calculation, he took almost like 4 weeks. So by the time event will be over. So that meaning is that it involves lot of computation. So this is called Richardson's forecast factory. If you want to solve the equation and produce the forecast in 6 hours, within 6 hours, he estimated like it is almost like 60,000 people all together simultaneously working together. Then only we could able to produce. So this is how he tried in 1930 and he published a paper in 1922. But this is due to many issues, like there are a lot of issues with the initial data, which is giving us the initial condition, imperfect initial data, and also our understanding of the model is very limited. So, and we were not having very big computing system to produce the forecast. So all these many type of error accumulated and resulted in the failure of the Richardson attempt. But by 1950, this has been attempted in the computer. It is known as ENIAC, electronic numerical integrator and computer. So that is actually this is belongs to US Navy, and that computer itself was commissioned during Second World War for nuclear energy research, nuclear weapon research. So after that, after the World War II is over, we got climatologists got some space in that computer, and they produce these 3 peoples like Charney, Joffort, and von Neumann. Von Neumann is a computer scientist. He made all these codes, all the mathematical codes. He ported in the computing system and produced the computer. So that means if you look at the ENIAC mission, it is occupying almost like 15,000 cores, 1,500 square feet of space, having lot of more than 30,000, 60,000 transistors and all. But if you look at the speed of that ENIAC, it is around 100 kilohertz. But our modern laptop and modern computers, the speed is 4.2 gigahertz. This is just a comparison. So that's why if you look at the forecast skill over the years starting from 1955 up to 1980, we can see that this is the skill up to 50%. What is the meaning of that? Skill up to 50% is not useful because it is worse than tossing a coin. So 50% accuracy is nothing but whether can occur or cannot occur. It's like 2 binary events, 50% chance. It is like tossing a coin. The probability of having head or tail is almost like 50%. So that means after 1985 onwards, the NWP skill has been increased drastically. Why it is happened? So if you look at the NWP skill over the years from 1981 to now, you can see that this is a skill of 3-day forecast, 3-day advanced forecast, and this is the skill of 5-day advanced forecast, and this is the skill of 7-day advanced forecast. What is the meaning of this? Because from 1981 onwards to 2000, the skill was drastically increasing. But after that, after 2000, the skill is getting saturated because this is the period where we got lot of satellite which measures different type of weather parameters from around the world. So that is contributed to the skill improvement, and the skill improved over the years is such that if you look at this point, this is 5-day forecast skill, which is around 80%, which is almost equivalent to 3-day forecast skill 20-25 years back. So that means when 25 or 30 years to 40 years back, we could able to forecast some event 3 days in advance. Now we can able to predict that event even 5 days in advance. So that is the meaning of this forecast skill improvement. So this is mainly contributed due to various aspects, which is nothing but the higher resolution of the model, model resolution, the grid resolution has been increased, and then the meteorological observation after the starting of the meteorological satellites, meteorological observation which is coming around the world has increased. The volume of observation has increased. And then also, of course, the supercomputing power has also been increased over the years. So that is why the skill improvement in LWP over the last 4 decades is contributed mainly from the technological advancements in terms of satellite radar. The observational capability has been increased so that more and more data set is coming from various parts of the globe. And then the supercomputing capability, the computational power has also increased. So these are the two contributing factors which happen in the technological advancement, which has contributed to the skill improvement in the weather forecast. So that is why we need supercomputers in India also as part of the mission Mausam, which is recently launched by the government of India. As part of this, we are getting 2 supercomputers like Arca and Arnima, which is occupying like 188, and if you look at the top 500 list in the supercomputers, it is going to occupy 188 and 189 positions. So this is how the India is also moving forward. And if you look at the weather prediction models, it is very difficult to construct a model because all this, if you look at this equation, and this is the unknown effects, frictional terms, and this in the thermodynamic energy equation, this H, the enthalpy, that is unknown. So this unknown process, which is nothing but these are the schematic representation of this unknown processes. This has to be represented in the equation. That is the tedious task. So if we are failing in representing all this real world process in the model, we will fail. So that is why we are constructing a model which is having lot of unknowns and uncertainties. So that is why that constitutes the uncertainty in our model predictions. So the uncertainty is mostly coming in our prediction is mostly coming from imperfect formulation of our model, because all this nonlinear process cannot be represented in a single term or with a single equations. So that is why we make some approximations. We do have some kind of empirical relationships, which makes this which is going to close all these governing equations. So and we don't have lot of data, heterogeneous data. Continuous data is not available, though we have satellite, but it is a kind of polar orbiting and geostationary satellite. It will not cover entire globe every time. So that is why the data itself is not adequate to initialize the models. So this is why if you look at the model world, this is the model world and this is the our model world, but almost if you compare it with the real world, it will not be matching anyway. So this is how, if you make a model, it is far away from the real world situation, the real world process. So that much difficulty is there in building a model. For example, within the grid box, there are a lot of physical processes happening. We have to represent all these micro scale processes in the equation. So this is very much important. So that is also another factor. And another thing is that we need to, if you want to predict weather over India, we need to know what is the weather over the Pakistan 2 days before. So that means the Pakistan weather. So if you look at this wave activity, the weather which is starting from Mediterranean Sea coming to the Pakistan, and next day it is reaching, it is moving towards east. So that means if there is any rain in the Pakistan 2 days before, that rain system will come to India 2 days after that. So that is why we need to know, we should have a bird's eye view of the entire synapses of the weather pattern at a particular time over the entire globe. So that means if you want to predict weather over US or China, we need to know the weather over India and weather over Pakistan. So this is so that is why we have to transfer all this data from around the world to other regions, other national agencies to make the weather prediction to work. So that is why it is under UN, and there is a framework for that. As part of that framework, this is known as WWW. It is known as World Weather Watch, where under the World Weather Watch program, there are three components: global observing system, global telecommunication. So because the technological advancement in terms of telecommunication, improved telecommunication, that is also contributing, because whatever data we are collecting from each region has to be transferred to other national agencies to make their predictions. So that means the fast global telecommunication network is very much important. And then after getting all this data, there is a global data processing and forecasting system which finally makes the forecast. So this is the workflow of forecasting system. It is a global effort. Actually, weather forecasting is a global effort, the collective effort under the UN framework. So that's why you cannot blame anyone for a wrong forecast, because it is a collective effort. The model is building collectively, the data is being transferred, and there are a lot of global cooperation happening. So this is, there are different heterogeneous data is coming, and there are a lot of recent advancement in terms of radar, satellites, and computing. So radar, earlier the radars are meant for just detection, but now with the Doppler capability, we could able to identify the velocity at which the rain system is passing, or cyclone is passing. We could able to from the Doppler capability of the radio waves, we could identify the speed at which the target is moving, in this case the cloud system. And another thing is that with advanced techniques like dual polarimetric techniques, like if you transmit the waves in the horizontal and vertical polarized form, we could get the structure of the cloud inside the cloud, how much the shape of the raindrops and the size of the ice crystals, hails, all this we can estimate. So this is how the technology is advancing. And the data, in terms of data, if you look at the archival of Earth data, it is around 72 petabytes in 2022. It is projected to be something around 600 petabytes by 2030. So that means there, if you look at the 4 V's of data, that is high volume, velocity, variety, and veracity, it is increasing in terms of, for atmospheric data we have 5 dimensions, right? For the spatial, 3 spatial dimension, X, Y, Z, and then 1 time dimension, and then nowadays another dimension is coming. It is known as uncertainty dimension or the ensemble dimension. So that the Earth data, the climate data is having a, in essence, a 5 dimension. If you want to handle this much data, the 5 dimension means the extra 1 dimension will add lot of huge volume of data. So this is how the data volume is increasing. It is actually a big data problem. So we have to handle this. And another way of advancement is in data assimilation, because there are different type of heterogeneous data which is coming from each and every corner, from different platform and different sensors, different type of observations. All this has to be combined together to produce the initial state of the atmosphere, from which we are actually making the forecast. That is why in the forecast formulation I told, if we want to predict the future state, we need to know the initial, what is the current state, and then what is the change of that value in the small time step. So that is why this observation is helping to make that initial condition. So that is the initial condition for the model forecast. So that we are doing with a methodology called data assimilation, where we try to club all this heterogeneous data coming from different platform, different sources, having different type of errors. We optimally combine together through some kind of least square techniques or advanced variational techniques, ensemble Kalman filters, or AAML techniques and all. Finally, we come up with a final analysis. From this final analysis, this is the initial condition. This final analysis is the initial condition which is available throughout the world, and from which we will try to issue the forecast. So this is how it is, and over the years we have earlier we were having standalone models like atmosphere only models, and then we combined atmosphere with ocean and then with the land with the CAs, and over the years if you look at the our evolution of our modeling system, each component of the model has evolved independently. Then after that, ocean first atmosphere model has evolved, and then after some time ocean model has evolved, and then ocean and atmosphere model combined together somewhere around 1970s. So that is the coupled models, and as time progress, each and some of the many modules have been integrated to the common platform that is constitute the Earth system model. This is how the modeling is evolved over the years. So earlier from the simple one-dimensional model or the energy balance model, and then now the most sophisticated coupled models, and then now even the biogeochemistry is also being integrated to the model that is known as Earth system model. So starting from the energy balance model to the Earth system model, this is how starting from 1960 onwards how the modeling system has evolved over the years. And if you look at the climate projections are not exactly the climate the weather prediction. It is a different concept because we have to it is a kind of different scenario for the future. We don't know what is going to happen for the future. So where we are devising different scenarios. Earlier it was representative concentration pathways. Now it is SSP, shared socio-economic pathways. So the socio-economic condition only will determine what is going to be the future. So that means now we are visualizing different type of socio-economic development. Some of the development which is very kind of fossil fuel driven, large developed condition, that will lead to a lot of uncertainty. Like rapid growth, taking a highway, it is like taking a highway. Every time there is a chance of if there is a chance of accident or collapse. So it is kind of very rapid growth stage. So like that, the scenario will tell us if you take this growth, you are going to end up like this. That is why if you look at the SSP 580.8.5 scenario, it is a kind of rapidly developing road with a lot of fossil fuel emission that will lead to a temperature state of around 4 to 5 degrees by 2100. Now it is just 1.2 degrees compared to the pre-industrial period. So that means if you take that road, it will reach to 4 degrees higher compared to the pre-industrial period. So then it is up to us to determine which road we want to take. So that is why the scenarios for the future is being developed. That is, and also in the weather prediction, there are a lot of uncertainty involved in it. And if you look at the uncertainty, like for example, and most of the uncertainty is coming from the initial condition, errors in the initial condition, imperfect model formulation. Now the numerics, the truncations, the approximation, everything is adding to the uncertainty. And then now climate change is also making a lot of uncertainty because the physical process itself, understanding of the physical process is also very much important. Climate change is making the physical process itself is more uncertain. So that means all this together is making the uncertainty. If you look at this problems, if you drop two balls nearby, but it will end up at two different positions. So this is uncertainty. Again, if you take these two balls and drop from the same position, one ball will go like this, another ball will go like this. So this is how the path uncertainty. So this is you have to deal with this type of uncertainty. In weather prediction is not an exception. That is why butterfly effect is there. It is like it's not like the saying is that a fluttering of a butterfly in the Mexico can create a tornado in the Texas, but it is not like it's an exaggerated version. But otherwise, what it is telling is that if you start initial state, it will go smoothly, and after that, the solution will be like with 2 or 3 attractors. So it is a kind of flattering of a butterfly eye, a butterfly's wings. So that is why it is known as the butterfly effect. And that is why in order to accommodate this uncertainty, we normally use kind of ensembles of model. Rather than a single deterministic initial condition, we produce lot of ensembles from these nearby initial conditions, so that what if we have only one more forecast, this one forecast for 48 hours will end up like this. But in the reality after that, if you look at the reality will be like this. So there are a lot of errors if we use only one model. So rather than if you use n number of initial conditions and issue n number of forecasts, meaning is that some of this model forecast that will come close to the observed state. So this is how, if you use ensembles, to some extent we can solve this issue by giving kind of probability forecast. So this is how it is advancing, and even a lot of AML based techniques are nowadays available, bias correction techniques are available, and recent Mundage event, this is a kind of forecast we have generated based on AML. So 3-day advance forecast for the MAPADI, 2-day advance and 1-day advance forecast. So that's why the forecast was there with the AML techniques. This is a raw forecast. 3-day advance forecast is showing something around this region, 1-day advance and 2-day advance. So with the AML we can correct and some of the errors, and we can produce a more reliable, consistent output for the MAPADI. So with this AML is going to be kind of promising for the future, because if you look at the application of AML techniques, it can be used for observation, correcting the observation, data assimilation, and numerical weather forecasting, both in physical formulation and numerics, and then post-processing, reducing the uncertainty and reducing overall bias in the forecast. All this can be done with AML techniques. So that is high. And another thing is that if you look at the total volume of the data which is generated from n number of satellites, there are a lot of satellites and any number of radars, lot of data is generated every day, every seconds. So if you look at the total number of received data, we are actually using less than 10% of the total received data. So we are not able to utilize the full data itself. So that is why AML is also going to have a say on this by having like a kind of unsupervised learning techniques to make use of this entire huge volume of data. And then it can be used to predict the formulation of the physical process. Formulation also can be used, AML can be used, and all the spectrum of post processing also to reduce the uncertainty. We can use AML. And nowadays the quantum computing is coming up largely, because earlier the computation, qubit based computation with a kind of binary, either 0 and 1, but the qubit based is values between 0 and 1 can be used, and so that the numerical errors associated with the forecast can be reduced to some extent with qubit based computation. So the quantum computing is also going to be another promising tool to be utilized. So these are some of the advancements we are visualizing in weather prediction, climate modeling. So actually the technological advancement which is happening around the world, we are the first beneficiary from all these technological advancements. The skill which we achieved over the years, which is contributed mostly from this technological advancements. So yeah, I have done with my talk.
What are some hands-on classroom activities or analogies which we can use to help the students understand about climate and changes? So you're muted.
Yeah, there are many simple experiments can be done. There are many online platform, KTOL or Kids for Climate Change from the NOAA. They have they have listed many activities as part of this learning process. So maybe you can visit those links. If let me see, I will share a few links where there are many educational resources available with respect to classroom teaching, especially the secondary or higher secondary classrooms. So it is many resources are available, teaching modules are available. So I will try to share that.
Okay, sir. Sir, you mentioned about use of fossil fuels rising atmospheric temperatures. So now, with the use of electric cars and green fuels, can we expect climate change to be reversed?
With the energy, because if you look at the 72 percentage of this emission is coming from energy sector, but energy transformation to this electric vehicle is not the only solution, because you look at the lifetime emission, means life cycle emission. In order to realize the benefit, it will take maybe another 50, 60 years to realize all the advantage of having the electric vehicles. Otherwise, if you look at the life cycle assessment, it is not going to solve immediately, because another thing is that carbon dioxide already emitted to the atmosphere, it can stay for another 100 years. So that is a lifetime. And the electric vehicle is not the only solution unless and until we are not producing the electricity to charge them from the renewable sources. So that will take time. So, and then another thing is that these electric vehicles are coming as alternative sources, which is not equitable, because it is not accessible to all. Because if you look at the price of this alternative energy and electric vehicles, it is not accessible for a common people. So, so emission is mostly coming from the developed nations. If they are not able to access that, unless and until China is not coming up with a low cost energy, means electric vehicles, we are not going to solve these issues. It is connected to economics, social, economic aspects as well.
Thank you, sir, for that. We have another question here. If the weather prediction is a global activity, why is prediction accuracy better in developed world in comparison to developing world, including India?
So as I told, it is a global effort, because whatever it is a US, Europe, India, Japan, all these nations working together to make the weather prediction around the world. So it is a global cooperation. But the thing is that the weather systems in the mid latitudes, especially the Europe and the uh, American region, which is having different characteristics. And if you look at the tropical region is a very chaotic region where the predictability is very less. So considering, as I told, the system, that is a target, the monsoon system, the tropical convective systems, somebody was putting the thunderstorms like that. It is a very small-lived, short-lived, small-scale systems. So in the Europe and all, it's a large scale system with a very big system, and the predictability is very high. So that's why they can predict. The signal is there already. The mid latitude, the developed nation, because fortunately, all the developed nations, they are coming in the mid latitudes. So that's why European predictions, and even we can also predict better for the Europe. The same European people cannot even predict better for India. That is why recently we have launched many projects, combined projects with the UK Met Office, NOAA, the US NOAA. So they are working with the Indian scientists to make better model for India. So this is how things are happening.
Thank you, sir, for that. We have one question from Ms. Shalu Jain. How can we sensitize students on this topic so they actually implement and know theories?
Yeah, a simple way to start with is that as I told, with a simple experiment. Another is that try to measure the local weather parameters, like simple. Try to start with measuring the rain, which is happening in their courtyard. So start with that, sensitize according to the weather pattern, and then you develop and try to analyze those weather pattern. So that there are many examples for that, because recently Kerala government has launched this weather schools, like weather observatories in maybe 250 schools. The students are taking weather observations, and they are getting sensitized. Not only students, in effect, the community is getting sensitized about the weather pattern. So this is the way to start with measuring the weather parameters locally and sensitize them the local weather pattern, and then look at the different academic modules to get them more aware about the global warming issues, the global aspects of it. So that is a way to approach.
Thank you, sir, for that. One last question. What is the scope of atmospheric science as a career, and what are the areas students should focus on to excel in it?
Because since climate change related issues are coming up, a lot of openings, but as I told, most of the jobs are in the US. A lot of Indians are working in US, and then the Trump government is shutting down, closing down many of the climate related labs. So that global that issue is there. But otherwise, it is a very means if you have passion for atmospheric and climate science, definitely it will become your profession. So that is what, if you, any subject, like any other subjects, if you have passionate about it, you mean students will have very bright future.